we're going to get started again. I'm going to continue from where I left off this morning, and that is as I did talk. So the next topic I was going to address today is a continuously stirred flow reactor. And particularly, I'm going to be looking for steady-state solutions for the continuously stirred flow reactors. And again, this analysis is from Obert, Peters, and Alcom. So this is the problem we are looking at. This is a reactor. Could be a continuously stirred flow reactor. The reactants come into this reactor, and this is the mass fractions. There's some fuel and air, a combustible mixture that is entering the reactor. Okay, m dot is the mass flow rate, so that many kilograms per second. The initial temperature of the reactants is Tu, and Yi is the initial mass fraction. So this quantity U always refers to the initial mass fraction. And then we have the product flows out. The same, so it's a steady state process. So therefore, whatever comes in is flowing out. No net accumulation of mass. And inside this stirred flow reactor, the temperature is T, and Yi is the mass fraction of the various reactants. Now, the chemical reaction that we consider is fuel goes by one-step reaction to products, and M is the mass. So M dot is the mass flow rate, and M is the mass of the reactants and products in this reactor, and the V is the volume of this reactor. Okay. All right. So again, as I already said, that the reactants enter at YFU and TFU. So as it is typical, we assume that what flows out, the mass fraction of the products that flow as Yi, and temperature is T. So what's flowing out here? Okay, that's the picture. All right. Okay. Now I'm going to write down the conservation equations, the balance. So really, what is the ultimate objective? The ultimate objective is to obtain the rates, to get the conversion, okay, to get how much is converted. This, again, is a very classical problem in chemical engineering, the stirred flow reactor problem. So you may have seen this. Any of you have studied chemical reaction engineering from Scott Fogler's textbook. How many of you have seen Scott Fogler's textbook? So this is actually discussed, this particular problem, in Scott Fogler's books on stirred tank reactors, except that in Fogler's book, it's done using numerical methods, but not. So what is new here is doing the same problem using asymptotics. Okay. All right. Okay. Now this is the balance equation for the fuel, or you can see that this is the rate of change of constant mass fraction of the fuel, and this is balanced by. This is the convection in. So you can see that m dot YFU is the amount of fuel that enters the reactor, and m dot YF is the amount of what exits. Okay, so therefore, this is the so that contributes to the change. Okay, and this is the rate of conversion. So this is the chemical reaction rate. So the net change of mass fraction of fuel in the reactor is balanced by convective forces in and out and chemical reaction. Okay. Now this is the energy balance equation here. Pretty much the same thing. Now we can see that this is the change of temperature. This is the change in enthalpy, this enthalpy coming in minus enthalpy going out, plus the heat release term on the right-hand side. Okay, the chemical reaction rate is written as a one-step process. So therefore, B is the frequency factor. And this quantity, rho YF WF, this is the concentration. So you can see that this is CF, the concentration of the fuel, written in terms of the mass fraction. All right? Okay. And E is the activation energy. And R, of course, is the gas constant. So then you have the balance equation for the fuel, balance equation for the energy conservation equation, and now we want to strive to solve a set of equations, okay, to get the conversion. Okay. Right, now again, as is typical on these problems, we need to, again, as I talked about asymptotics, the first thing we got to do is to non-dimensionalize the set of equations, okay? So that means I need to get in a characteristic time to non-dimensionalize this, and also a characteristic fuel mass fraction, so that so both these things are of order unity. Now, so what is this actually tells you what the characteristic time should be, because m dot is the mass flow rate, that's so many kilograms per second flowing in, okay? And this is the mass in the reactor. So therefore, m divided by m dot, in fact, if you take the m dot and put it in the denominator here, m divided by m dot should be the characteristic time, okay? So in this problem, and which is what it is. So you define a characteristic time as T nu, which is the residence time. This quantity T nu is m divided by m dot, okay? So I've now selected the characteristic time, and you can now I divide by this initial mass fraction of the fuel, so therefore you can see that this quantity y is 1 when it enters. So this is normalized, and the temperature is written that way, T over Tu, initial temperature. So therefore theta is 1 coming in. This is the activation temperature. Okay, this is the activation energy, E over R. That's the activation temperature divided by T. So that's the non-dimensional activation temperature. And this is the heat release. You can see that the heat release QF-YFU is the heat release in the reactor. That's the QF is the heat release per unit mass of fuel multiplied by YFU. So therefore that's the heat release, and is divided by the thermal energy of the flame. Okay. So in the reactor. So these are the non-dimensional quantities that you employ, right? So now you put all that in that equation, and now you get this non-dimensional equation here. So this is the mass conservation equation, the species balance equation, and this is the energy conservation equation. You get two equations, right? Again, some of these, all right? Okay. Now, Foreman in the previous lecture talked about what's known as coupling functions, right? He talked about how you can, you have energy conservation equations, the species balance equations can be coupled. So therefore, if you look at this particular equation, I mean, there's a source term that appears. So one can actually, if you simply add this and this, if you add these two terms, then the source term, which is the most nonlinear expression in the equation, this drops, okay? So therefore, now you define a new quantity, a coupling function theta, and this is very similar to what Foreman talked about last time. He had this quantity beta and alpha, and so now I'm calling that theta. So that's the coupling function. You define a quantity theta in this particular form, okay? And then what happens is, if you add these two equations, you see the chemical reaction term drops, so you get this expression for the coupling functions. So this is obtained just by adding these two and employing this assumption, all right? So that's the coupling function, theta. Okay, now what are the initial conditions for that? You can see that theta must be 0 because theta is defined this way. The temperature, the reactants enter, when the reactants enter, theta is 1, y is 1. So therefore, this quantity is, this watt theta is 0. So these are the initial conditions. So the initial conditions are at the entrance of the reactor, theta must be 0. So now if you take so therefore if you take this simple first order differential equation and you integrate that, one obtains this trivial solution. So theta is 0 everywhere. The watt theta is 0 everywhere. That's the trivial solution you get, okay, for this equation. Okay, so essentially taking that with the boundary condition that I'm sorry, this should be a tau. So there's a mistake. This is not theta, but this is a tau. Okay, you want to correct that. So that's a tau. Tau equals 0, theta equals 0. If you want to solve this equation with those initial conditions, the answer is that theta is 0 everywhere. Okay. So now you can immediately see that I can get a relationship between the temperature and the fuel mass fraction. Okay, so you get this relation. So this holds everywhere in the reactor. So therefore, now instead of solving these two equations simultaneously, I can select one of these equations. I can take this one, okay, and whereas this y, if I write y here in terms of theta, I can rewrite this, obtain y as a function of theta, and put it over here. So now you get an equation only in theta, the energy conservation. So this can be integrated. This equation is only for the energy. Once you solve for theta, I can use these coupling functions to get the y. Okay, that's the approach, right? Okay, so that's what I've done here. I've written theta in terms of y. Okay, now there's some interesting things you can observe immediately. Okay, the first is so let me just write down this theta. So you have this, so this was theta, okay. You get, that's 1, okay, with the coupling function is 1 minus theta plus q times the 1 minus y. And as I said, that theta is 0 everywhere, okay? So you get this relationship, you get this next relationship here between, so if you can see that theta equals 1 plus q minus qy, okay? Now you can, so now you can look what should be the maximum and minimum values of this quantity y, all right? So when the reactants, so the maximum value for this theta, the temperature is 1, because when the reactants are entering the reactor, y is 1. Since y is 1, theta is, so these two terms cancel, so theta is 1, which is the minimum value, okay? So that's the temperature at which it enters. Now what is the maximum value it can have? The maximum value this can have is when y is 0. That means all the fuel is completely consumed, okay? If it's all completely consumed, then the maximum temperature attained is 1 plus q. But of course, in the reactor, we do not say that all of the fuel is consumed, so only partially consumed, okay? So therefore, the value of theta is bounded between 1 and 1 plus q, okay, the maximum temperature, all right? And now here, so now this is a balance, so now I go back and rewrite this I'm rewriting this equation, okay? I can rewrite this equation in this particular form. That's theta as a function of tau. You can see this is what appears on the right-hand side. So, and this quantity n is this, okay? So this n is simply this expression with, if I take y and write y as, replace this y in terms of theta, so this is what I get, okay? So this is the energy conservation equation, where this quantity n theta is given by this expression. Okay, any questions on this so far? So I want to proceed only after you understand these set of equations, okay? So the point here again is that this is the energy conservation equation where n is given by that expression, okay? And the initial conditions are that at tau equals 0, theta is 1, okay? So that's the equation, all right. Now we are looking for what's known as steady state solutions. I mean, and this is a typical problem again in chemical engineering. You want to look at the steady state operation of this reactor, okay? So the system has reached steady state. System has reached steady state. That means this this term has disappeared. Okay, there's no net change in temperature, right? So that steady state expression means that the right-hand side is 0. So this is the steady state solution. So this tells you, this expression tells you that this expression tells you the temperature, steady state temperature. And what appears in this equation is this quantity called the Damkohler number, which I didn't tell you earlier. Again, this is an important parameter in combustion. And this quantity called the Damkohler number, you can see the Damkohler number is a ratio of a flow time. So this is a flow time, and B reciprocal is the chemical time. Okay, so for this Damkohler number is a flow time to a chemical time, and as we shall see later on, this plays an extremely important role in combustion problems. This Damkohler number, right? Okay. So now, if you look at this particular equation, you can see that this is an equation of a theta s, which is the steady state temperature in terms of the Damkohler number. Okay, right? So that's what that equation is. Okay. Okay. Now here is so these are again numerical integrations. So what we have done here is this is again done by Norbert. So these are numerical integration of the full set of equations. So this is the solution of these two coupled equations. Right? So this again, this is not asymptotics, but the full numerical integration. So when you numerically, so this E here is actually theta S. I'm sorry, E is the activation temperature, theta A. Okay, and this Q is a small q. So this capital Q is a small q. E is the non-dimensional activation energy, and Ts is the steady state temperature. Okay. So what this particular graph gives you is simply is this basically that, okay, plotted here, okay. So it's essentially what you do. You select some activation energy, okay. You select a value for the activation energy because that's chemical reactions. You select a value of E, and once you select the value of E, you can construct these curves. All right? Okay? So now, you notice something very interesting here. You can see that if E is 2, the non-dimensional activation energy is small, all right? You can see that the steady state, by increasing the Damkohler number, and what does increasing Damkohler number mean? One, how do you increase the Damkohler number? You can increase the Damkohler number by 2 ways. You can increase the Damkohler number by increasing the flow time, okay? So how do you increase the flow time? The way you increase the flow time is by flowing the reactants at a slower speed. If you slow down the speed of the reactants into the reactor, okay, that's a longer residence time. Okay, so therefore that increases the Damkohler number. Or the other way to increase the Damkohler number is to increase the rate of the reaction. So two ways you can increase the rate of the reaction, or you can decrease the flow rate into the reactor. Okay, and that particular this ratio is that is important, which is the Damkohler number. All right, so essentially, so this is what you're doing here. When you increase the Damkohler number, you are increasing the rates of the reaction. Okay, if you increase the rate of the reaction, it seems obvious that the temperature must increase. Okay, like that, right? Okay, and then you can see here. But another interesting thing happens here. You see, if you start, so this is what this value of E. Now, if the activation energy is sufficiently large, if we take a large activation energy, then you notice that the temperature goes down like this. Okay, this is the temperature rise, and suddenly at this point it turns around. Okay, and then it does that. So what that means is, so this is ignition. So this is actually a typical ignition problem of the reactor. Okay, so at this Damkohler number, so the reactants are coming in, and suddenly it ignites. So there's a rapid formation of the product. So it goes discontinuously from here to there. So this is an ignition phenomenon. Okay, right? On the other hand, let's say if you take so now let's say once the reactor is ignited and you have a rapid conversion, all right, then you start to decrease the Damkohler number. And the way you decrease the Damkohler number is by increasing the flow rates of the reactants inside, or decreasing the reaction rate. Okay, well, typically okay. No, it's not. Damkohler number is the way I've defined it here is this way. No, okay. But anyway, go ahead. Yeah. No, I think you always select the Damkohler number is usually based on the, even if you put the concentration, we usually put only the initial concentration of the field. We do not put the instant. The point is, in asymptotic analysis, the parameters that appear should be standalone, okay? It should only depend on the initial concentration of the fuel or the initial concentration of the reactants. You're not allowed to change that, you know? Okay.
So for the Damkohler number, that TB that you have taken,
yeah,
that will be the flow, that will correspond to the flow velocity, or
yes,
that will be the AD turnover time?
No, all these flows I'm looking at is typically laminar flows. So what that T nu is simply the mass, the instantaneous, the mass m divided by m dot. Okay, m is the mass, total mass of the reactants and products inside the reactor, and m dot is the flow rate. So this has units of kilograms per second. Okay, kilograms per second, and that is just kilogram. The ratio is the time. Okay, right. So that's the resonance. So so that's what I mean. If I increase m dot, that you flow the reactants at a faster rate, okay, then you can see that T nu, the react TV, okay, actually decreases, right? Okay, and therefore that means there's less time for the reactants to react in the reactor. If you flow it harder, faster, it doesn't have, it just flows out. It doesn't have time to react. Okay. Right. Yeah. I mean, it is, see, the point is that the Damkohler number can be experimentally controlled. You can control the Damkohler number, okay? So therefore, yes, I mean, in that sense, yes, because I changed the boundary values. Yes, it changes. Okay, but it doesn't. It's not a variable in the equation. It's a constant. Okay. So now you notice that the if you have now that the system is ignited, now if you have this, if the system is there's a rapid conversion, now after the conversion takes, then I decrease the dam column number. Okay, if you decrease it, one way to decrease the dam column number is to increase the flow rates. If I start increasing the flow rates into the reactor, then you can see that the dam column number decreases. It starts to move down this way, and when it reaches this point, it cannot. This part of the curve can be shown to be unstable. Okay, so now it continuously moves from here down. So this is called the ignition and extinction process, basically. Okay, so you can see by increasing the dam column number, there's ignition of the reactants, and by decreasing the dam column number in this direction, there's extinction. All right, but however, you notice that when the activation energy is 2, we do not have ignition or extinction. It just continuously increases. Okay. And then now you notice that when E is 5, it has a point of inflection. I mean, you have both the I and Q, they both coincide, and therefore you have a point of inflection where the second derivative is 0, okay, of Ts versus that, and therefore the curve. So this here ignition and extinction have merged. Here the ignition and extinction does not happen. Here there's ignition and there's extinction process. Okay, that's the point. So the point is that all this can be controlled by the activation energy, basically. The activation energy plays a role, right? So that's the point, okay? Okay. All right, so now I'm looking at, since we're interested in ignition and extinction, I'm going to do the following. I'm going to say at this point, okay, where the quenching occurs, either this point or that quenching point or the ignition point, you can see that the derivative of temperature with respect to ds, okay, this particular thing, d theta, dA, d theta s must be 0. So this is true at this ignition point as well as extinction point. Okay, so the derivative must be 0. So now you can take this particular, you can take this equation and take the derivative of this. All right, differentiate that. So that's what it is. I take that and differentiate that. Okay. And then again, what I've done is rewritten. So this is, I've taken this equation, written the dam column number. Sorry, like this. That's the dam column number. So I'm going to take the derivative dA ds, take the derivative of that, and set it equal to 0. And if you want to know how to do it, take the derivative of this. A nice trick to take the derivative is to take the natural logarithm. So you can write that as log dA equals log theta s minus 1, okay, minus log of 1 plus q minus theta s, right? Okay, times x times minus plus exponential, sorry. So that's simply theta over theta s, okay. Theta over theta s, okay. Now I can differentiate that. So to differentiate, as you get 1 over dA, dA, d theta s. And if we differentiate that, one is going to be 1 over theta s minus 1. So it's going to be 1, so that makes it a plus. So it's going to be 1 over 1 plus q minus theta s minus theta over theta s squared. Okay? So now you set that equal to 0. If you set that equal to 0, it's possible, so you get this simple algebraic equation for theta s. Okay? So this is at the turning points, basically, okay? So now this can be solved. You can get that two solutions to this equation, and this is the solution to that quadratic equation, all right? So essentially what I've done is I've obtained a quadratic equation from here, and then solve that quadratic equation to get this expression here, all right? So now this is something very interesting you can see here. Of course, there are two solutions, depending on there's a plus or minus sign, right? Now what you notice is that this particular for theta to have two solutions, both ignition and extinction, all right? It is necessary that that can happen only if this discriminant is greater than 0. If the discriminant is greater than 0, you have two solutions to this quadratic equation. If the discriminant is equal to 0, there's of course one solution. So that refers to the merging of the ignition and extinction point. And then the discriminant is less than 0, then there is no solution, and that refers to the continuous curve. Okay. So therefore you can see that now two solutions for this. Okay, discriminant being greater than 0, and then so now you can see that for this particular condition, if Q, which is the heat release, okay, all right, Q, if you recall, is the heat release in the flame, in the reactor heat release. So I can, if I know the initial concentration of the fuel, if I know all this, then I can compute Q basically for that particular system. So you can see that if Q equals 4, okay, if I select the value of Q as 4, then you obtain the relationship that when the activation temperature is greater than 5, there are two solutions possible, okay, for this. So therefore, if activation energy is greater than 5, you have both ignition and extinction, all right, if the ignition and extinction collapse, if the activation energy is 5, and for theta less than 1, there's no abrupt ignition extinction. Now this exactly agrees with this particular formulation. You can see that here. The E is actually theta. So when E is theta, the ignition and extinction is collapse. When E is greater than 5, you have ignition and extinction. And for E less than 5, this is one solution to that equation. All right? Okay. Okay. So therefore, so now again, this goes back to this. I had a question earlier. The point is in asymptotics, we always look at the extremes. So how good is the extreme? Okay. Now this answers this very well. For example, now you can see that. Okay. All right. So what I've done here is, okay, I mean, I didn't discuss this one. Okay. So I just took this solution here, okay, and put it over here, and then I want to look at the asymptotic limit when theta is very large. What happens if the activation energy is very large? Okay. And now we have both. Okay. When activation energy is very large, you can see you can take this particular equation, all right. And you can approximate this, right? This is simply a simple Taylor series expansion. So the square root of 1 minus this quantity is 1 minus 1 divided by 2. Okay, the first term in a Taylor series expansion is simply 1 minus this quantity divided by 2. So you can write this numerator as this for large values of theta A. Okay, and I can write this denominator, which is 1 plus QA, as 1 minus, again, a Taylor series expansion for large theta. And if you put all these two things in this particular equation, you can solve. You can solve for. You get this particular expressions. Okay, so they get a theta. If you take a plus sign or a negative, the plus sign or the negative sign will correspond to these two solutions for theta at the turning points. Okay, right. Now what you notice here is that this is the quenching. So you can see that. If you go back, if you recall, the maximum temperature in the reactor was 1 plus Q. So when the system is quenching, you start from the okay. So if I have this particular expression here, okay, we had something like this. So the maximum temperature here, the asymptotic temperature here was 1 plus Q, okay, and this one over here was 1, okay, basically 1. The minimum value of the temperature was 1, and this is the Damcolor number. So you can see that. So this is so if you are in this if you are in this part of the curve, the maximum temperature is 1 plus Q, and if you start decreasing the temperature along, so that means if you decrease it by this amount. So the point here is that the point here is this distance here, okay, is 1 plus Q squared over theta. 1 plus Q squared over theta. That is this distance here. Okay, that corresponds. So the point here is that if you have a reactor where the maximum temperature of the reactor is 2000, which corresponds to the maximum temperature. Just by decreasing the temperature by 200 degrees, it can lead to extinction, okay, for the large activation energy problem, right? And this is the ignition. So therefore, now you start with 1, And then if you increase the temperature by 1 over, so this is a 1 over theta A, okay? So if you increase the temperature by a small amount, here, theta A being very large, just by increasing the temperature by a small amount, one gets ignition. So you can see that the process, because of large activation, it's only a slow rise in temperature, and then there's a sudden jump, okay? A sudden jump in temperature. And then on the same side, if you have a steadily operating reactor, there's by increasing the flow rate, there's a small drop in temperature, and then again discontinuously, the reactor extinguishes. Yeah. So this particular behavior is only possible for large activation energy. Yeah. That is unstable, yes. This particular region is unstable. It is mathematically defined. I mean, you take this equation, and do a small perturbation, okay? And you see how the perturbation grows. If the perturbation, once you perturb the equation, if the perturbation increases exponentially, then that is unstable. If it does not, then of course, then that's a stable solution. Okay, these are things called the. I mean, if you look at if you put these equations, what's known as a phase space. Okay, analyzing the phase space, you get what is known as saddle point singular. You get what's a nodal point singular, unstable nodal point singularities, and stable nodal point singularities. And unstable nodal point singularity, all the integral curves will move away. Okay, the stable point singularity, they all will move in. So it depends on. So you can analyze the stability problem that way and see whether the integral curves go out or the integral curves come in. Okay. Right. Right. Okay. Any other questions on this? So now the key point I want you to I appreciate a few things. Okay. And again goes back to some of the questions that were raised in the previous slide. First, there was a question before what is the reaction zone thickness depends on. Okay, what the thickness of the reaction zone versus so the key point is you see the point here is that the Damkohler number. Which is defined with this quantity. Damkohler number is actually, if you look at this point here, the Damkohler's number is large. For this integral curve, if you could look at this curve as well as this curve, they have a solution for a large Damkohler number. But it turns out only the one which has a large activation energy exhibits this quenching, ignition, and extinction phenomenon. A system which has low activation energy does not have that. So the key point here is the activation energy must be large for the systems to exhibit ignition and extinction phenomena. Okay, that's the point here. Okay, it's large, not the large Damkohler number; it's a large activation energy. Okay. And this is a very important point. Okay, all right. So now we established that. Okay, and we established that from this particular. If we see that theta has to be large, greater than 5 to exhibit that. If it's less than 5, then you do not get abrupt ignition or extinction, right? Okay. Now what I want to do is analyze, to look at the behavior and what happens. So now I want to look at this. I want to demonstrate that when will the curve do this? Okay, maybe I should take it out. Okay. So I want to demonstrate the following. Now I'm going to look at particularly this point here, this point. And look at this curve and ask the question, when will this do this and when will it do that, okay? Like this, okay? So the idea is when will it quench, okay? So, when will I get this behavior? No, I'm erasing everything. When will I get this behavior, okay? And when will I simply, so I'm going to look at, do a perturbation analysis, an asymptotic analysis in this limit, okay? I'm going to consider a system which is over here, and then look for large and small activation energies and try to demonstrate how look at the behavior. Okay, so this is what I've done here. So I looked at okay. All right. Okay. So yeah, sure. So now I'm going to look at the critical conditions of extinction. So now, as I said before, the temperature drop is very small from here to here, okay, before it extinguishes. So I'm going to perturb the temperature. I'm going to say that take the temperature, steady state temperature, theta S, is 1 plus Q, which is the maximum temperature, minus a correction. Okay? So this epsilon Z now is going to be, so if I, for example, epsilon Z is just going to be this distance here, okay? This distance is going to be epsilon times Z. And this is 1 plus Q, right? You look at the, so that's the, the Z is a variable, okay? So Z is, I'm going to allow Z to change so that I can go around this curve, okay? So now, again, this is us just to, so I can write 1 over theta S as this. Now now again, this is an asymptotic expansion. It is again a Taylor series expansion. This Taylor series expansion is a, okay. So it's actually 1 over theta S, okay? I can write that as 1 over 1 plus Q, right? Minus epsilon Z, right? So therefore that's going to be equal to 1 over 1 plus Q. I'm going to take that out because of order unity. 1 minus epsilon Z by 1 plus Q. And you can do a Taylor series expansion on this one, so it's going to be 1 over 1 plus Q. Now you can, so that's going to be 1 plus epsilon Z over 1 plus Q. Okay? So I just take the leading term. So therefore that, if you look at that, so that's exactly this. Okay, so that's 1 over theta S is written this way. So therefore this particular equation, 1 minus theta S, this particular equation, now is written, can be written in this form. So all I've done here is simply replaces theta S by this, okay? And then the exponential term in N of S is written, the N of S as an exponential term, okay? Which is this, all right? You can write that as, so that's what, so this is how it's written, okay? Now let's look at this particular equation, right? Now in this equation, we know that epsilon, we said that epsilon is very small, okay? And epsilon is small, and so therefore, in this particular equation, this term can be dropped. So therefore, this, I can drop this immediately, okay? So now I have a balance, so I have this equation, and I have this equation, okay? These two terms are balanced. Now I'm going to consider two cases. I'm going to consider the case where the activation energy is large and the activation energy is small, to illustrate why activation energy must be large. All right. If you take the case, if you take that epsilon is very small, okay. I'm going to take the case where theta A is of order unity, or these are two cases I want to consider. Right. So let's look at this particular case. The first case is theta A is of order unity. Okay, I rewrote this equation. Right, with that epsilon A term dropped. Now, for theta, for this case where the activation energy is small, okay, not large, then here you can see this particular expression that appears dA times epsilon. So I can select epsilon, okay, the expansion parameters. I can call epsilon as, I can select it this way, okay. If I see that epsilon is reciprocal of the Dam-Polar number, then this term becomes of order unity, okay? Now I can see that I can drop this term because theta A is of order unity and epsilon is small, okay? Therefore this term drops, so this is the solution. So the correction is given by this expression, okay? So that is Z. So therefore, the one thing you know is that, so you can see that, so this does not exhibit ignition or extinction. So because this is continuously, there's that is the expression for a Q. Okay, for Z, for example. Okay, so this is the so-called large Dam-Polar number asymptotics. This large Dam-Polar number, this is Z. Now, and the temperature is now given by this equation. Okay, right? So this approximates the upper branch of the S-shaped curve, but for small values of activation energy, which is like 2. Okay, so that's that. So it actually reproduces the curve which does not have turning points. On the other hand, if I assume that the Dam-Polar number is large, if I assume that the activation energy is large, okay, you can see that now I can select the epsilon such that I can select epsilon because activation energy is, this is large, this is small. You can assume that, you can say that the product must be of order unity. So you can select epsilon as this. If you select epsilon as this, you get this particular expression, okay? Now, here's this expression of the damp dA. So this equation. So you see, if I select now, if you look at this particular term here, dA epsilon, if you select epsilon equals 1 plus q squared over theta a, you select this. So I'm selecting epsilon in this fashion such that this becomes of order unity. Now, if you put the epsilon over here, okay, then you get dA times 1 plus q squared over theta a. Okay, then it follows that this particular thing should also be of order 1. Okay. Otherwise, if I do not take that to be of order 1, this entire, if I take that to be too small, then this term will drop. If I take it to be too large, then of course it cannot balance because you have to have too large a quantity being equal to 0. Okay, so therefore it's necessary to select this particular expression to be of order 1. So this is both large damp Coulomb number and large activation energy. So you have two. This is the distinguished limit that I talked about in the heat transfer problems, where you had when you had the Prandtl number and the Reynolds number, and we looked at the limiting for Prandtl number. If you had a distinguished limit, so here you have a distinguished limit of large activation energy and large damp Coulomb number, and you have this distinguished limit. Then you can then you can see that this equation, this particular equation takes this form, okay, in that distinguished limit, and then if you plot that, you get this turnaround curve. You get this. So this is lower branch is the this is actually the upper branch, okay, and then it turns around, and you get this extinction curve, okay, the quenching point. So the important message here is to have ignition and extinction phenomena, two things should be large. The damp Coulomb number must be large, and the activation energy is large. Okay, large damp Coulomb number. If you have only large damp Coulomb number and not large activation energy, then you do not get ignition or extinction. Okay, and that's the clear demonstration why they both must. A distinguished limit is required, and you can see later on when we talk about diffusion flames are always in this distinguished limit of large damp Coulomb number and large activation energy. Okay. Right now we can go a step further, and on a step further, I can say that I can find out that at this turning point, you can go from that equation. You can see that at the turning point, this is from this particular equation, I can get that at the turning point, delta must be equal to epsilon and z equals 1. Okay, so now if you recall that delta is okay, delta is given by this equation. So when I put this equal to 1, okay, then you can determine at what damp Coulomb number will the system extinguish, right? Okay. Now, so by the way, I want to point out that if you go back, for people who have studied from Scott Fogler's textbook, okay, you should go back and take a look at that. There are many homework problems on CSTR, continuous stirred flow reactors, okay, and a lot of those problems you are asked to do it numerically, okay, either numerically or for example they ask you to calculate the conversion. Now you'll notice that I've done that. I've told my students how to do that, so I think you should do that yourself. You can take many of those problems you've already worked out, okay, and you try to do it using this asymptotic formulation, and you'll find that you can very quickly get answers to almost entire 10 or 15 problems. You can do that with your hand calculator, okay, and get very accurate results. Okay, so every problem in the textbook which has large activation energy can be done using this method. Okay, so that's the first. This is what I want to do this morning. I'm going to move on to the second lecture. All right. Okay. All right. So that's this is what I was supposed to finish. Okay, we do lecture 2. So I'll try to be very fast here. Okay. Now here I'm going to, in the previous talk we talked about applications for asymptotic analysis of fluid mechanics to heat problems from heat transfer, and I saw how it's possible to simplify. We looked at a we looked at a thermal ignition problem, okay, where you saw there was a balance between heat loss rates and heat generation rates, and we were able to get the ignition delay time, okay, and the criticality condition. Then we looked at the non-thermal ignition of hydrogen, and we were able to get the important concept there was the crossover temperature. Okay, you had this crossover temperature. If the temperature of the system is greater than the crossover temperature, then ignition is possible. Otherwise, it's not. Okay, and in this reactor problem, the last one, an important lesson there is that it is necessary to get large Damkohler number takes you to a nice burning system. A small Damkohler number is something where the system is not, it's low reaction, okay? And to get ignition and extinction phenomena, you must have large activation energy, okay, and large Damkohler numbers. So that's the key points which I wanted to, So I'm going to put all those ideas which we have developed so far, I'm going to use that to analyze problems in combustion, all right? Okay. Right, here, okay, now, the asymptotic, I want to give you a rough overview of asymptotic analysis. Asymptotic analysis of flame structure, there are basically two types of asymptotic analysis. One is called the activation energy asymptotic analysis, okay? AA. And the other type of asymptotic analysis is something called the rate ratio asymptotic analysis. Now, what is the important difference between them? In activation energy asymptotic analysis, the chemical reaction is approximated by a one-step process, fuel plus oxygen going to products, okay? And we will, and in almost all problems in combustion, it can be clearly, it turns out that activation energy is indeed large, okay? So therefore, so using one-step reaction with large activation energy, okay? But it turns out that if you look at elementary reaction rates, of course, so these are global reactions, one step, okay? Now, if you look at elementary reactions, it'll turn out that the activation energy is really not that large, okay? So the question is, so how we justified are we to use large activation energy analysis when in reality the activation energy is actually small for the turns, and that is addressed here in the rate ratio asymptotics. In rate ratio asymptotics, the activation energy is not presumed to be large. Okay, so this is basically large Damkohler number asymptotic analysis, and that is large activation energy asymptotic analysis. And I just said said a few minutes ago that if you do not have large activation energy, you cannot get ignition and extinction. Okay, but that's only for a one-step reaction. Now, in rate ratio asymptotics, we'll have multiple step reactions. When you have multiple step reactions, that restriction no longer applies. You can still have low activation energy and still be able to predict have ignition and extinction. But for that, it's necessary to have multiple steps and not single steps. Okay. So this is what I want to talk about later as well. Okay. Now, what is common in both? What is common in both is that both use singular perturbation techniques. And I talked about it when I talked about fluid mechanics. I talked to you about regular perturbation analysis as singular perturbation analysis, and both of them are singular perturbation. Is in that you lose the ability to satisfy boundary condition. So to be able to satisfy the boundary condition, you have to force certain terms in. Okay, and that's the problem becomes singular. Okay, and then of course they both will have there'll be an outer solution and an inner solution, and then you have to do matching. So this is classical boundary layer theory, basically. Okay, as applied to reacting flow, right? Okay, now I'm going to demonstrate application activation to premixed flame, non-premixed flames, and later on to rate ratio asymptotics to premixed flames and non-premixed flames. And eventually, okay, now here's the question. Now there are many problems where activation energy asymptotics actually works very well. Okay, even though, as I said, the rate, the reaction rates are small, the question is why does activation energy asymptotic work? And it turns out, yes, there is a relationship between. I'm going to try to relate these two analyses, and you'll find that there exists a relationship between the both. Okay, from rate ratio asymptotics we can derive an apparent activation energy, and that apparent activation energy is actually large, right? Okay, right. So now, so this is a simple laminar flame theory. So this is so-called phenomenological analysis. So the first topic is going to be premixed flames. I'm going to talk about premixed flames, activation energy asymptotics. Okay. So let's consider a premixed flame propagation. So this is a premixed flame, but so this is a reactant. This side, okay. The reactants are entering in at some temperature TU, and the flame is propagating in that direction. Okay. As you know, these problems have translational invariance, all right? So therefore, you can put the the origin anywhere you want because there exists this translational invariant. So therefore, there's a reaction zone, thickness delta, and that's where that's okay. Now delta is the thickness of the wave. VU is the burning velocity. TU is the initial temperature, initial density. TB is the adiabatic temperature. Q is the heat release. WM is the rate of mass consumption per unit of the reactant mixture per unit volume. Okay, that's important to know. Okay, Cp is the heat capacity, thermal conductivity, and that's the Lewis number. In fact, this particular analysis, I'm going to assume the Lewis number is 1, so this is not really relevant here. But these are important ones. Okay, all right. Now let's look at this reactant mixture. Okay, now you can see that the wave is adiabatic. Okay. So whatever heat that is, the point here is that whatever heat that is released in this reaction layer has to be conducted upstream, right? Because here it cannot be conducted in the other direction because that's the post-flame zone. So all the so the chemical reaction takes place and the heat that is released is conducted upstream in this direction by thermal conduction, right? Okay. So wave is adiabatic, so the heat release is equals Cp Tb minus Tu. Okay, that's just straightforward. Okay, right? Now the rate of heat release per unit volume per unit time, as I said, this is the Q is the amount of heat released per kilogram of the reactants that is consumed. Okay, and this one is the reaction rate. All right, so this has units of so this is joules per kilogram, okay, and so this has units of kilograms per cubic meter per second, okay. So therefore, this has joules per cubic meter second, and you multiply by the wave thickness, okay. So therefore, you get this heat release per unit area per unit time. So this is the heat release per unit area per unit time, okay. So that heat, as I said, that is heat release per unit area per unit time is conducted upstream. And the upstream conduction is written this way, lambda dt dx, and that is simply that, okay? So the idea of this is a very rough, that's why it's called phenomenological. I simply assume that it's a linear, okay? It goes from just a straight line, okay? So that's the heat conduction upstream. So now you can equate this to this, okay? So you can equate that, and immediately from this equation you can see that you can derive the thickness of the reaction zone. So the thickness of the reaction zone is given by this particular expression, thermal conductivity, heat capacity, and the reaction rate. You can get that immediately, okay? Right? Okay, now, so that's the thickness of the reaction zone. Now the rate of consumption of reactant per unit mass per unit area. So as I said, that this is Wm, has units of kilograms per meter second, right? So that's that's Wm is kilogram per meter cube, okay, second, okay. So now delta is of course the delta is the thickness that has units of meter, and that must be equal to rho u vu. Rho u is the density of the incoming reactants, and v is the flame velocity, okay. So therefore this you can say is kilograms per meter cube, and this is meter per second, okay. Therefore the units match, okay. So therefore you can see that the this W delta is rho u vu, but from the previous expression we showed that delta is actually this. Delta is given by this expression. So for now we equate these two, we can get the burning velocity. So burning velocity has this particular form. With the burning velocity, there's a reaction rate that appears, okay? And therefore it's the square root of the reaction rate. The burning velocity goes as the square root of the reaction rate. Is proportional to the thermal conductivity, inversely proportional to the heat capacity. Okay, so this is a very simple expression that you get from you can get the functional dependency. The very simple expression for the burning velocities in terms of the reaction rates, right? So now we've got the flame thickness as well as the burning velocity, right? Okay, so now you can go a step further. You can know that the chemical reaction rate can be written in this particular form. It has a pressure to the nth power, depending on if it's a biomolecular reaction or unimolecular, whatever you consider, okay? And that's E over RT. So now you get this burning. So now you can see that the flame thickness goes as the P to the minus n by 2, and the reaction. So this is the reaction zone's thickness. It goes as the pressure raised by minus n by 2. So basically, this is so the phenomenological analysis tells you, gives you lots of information. Tells you how the burning velocity depends on the reaction rate. It tells you how the flame thickness depends on the pressure, and also how the flame thickness depends on the reaction rate. Okay. So this is a very rough estimate of that. Okay. Now I'm going to go further. Okay. Now I'm going to go a step further and to try to derive this, do it more accurately. Okay. Instead of making this very simple approximation, try to act more accurately using asymptotic methods. Okay. Right. Okay. All right. Now this. The theory, what I'm going to talk about here is the theory is based on the theory by Frank Kamenetsky. Zeldovich was actually formally obtained by Zeldovich and Frank Kamenetsky. So they were the ones who actually, the idea of, the basic fundamental idea of using large activation asymptotic analysis to solve combustion problem actually comes from Russia, and the key players are Frank Kamenetsky, that's what I write here, and Zeldovich. Okay. Right. Okay. Now it turns out the Bush and Fendel, and this is something every student must read. Okay. Now, you should write it down and you should read it. Okay. This particular paper by Bush and Fendel in the Combustion Science and Technology, it was published in 1970, which is one of the first very careful and detailed and complete analysis of asymptotic theory as applies to laminar formulation. Right? It's a classic paper, Bush and Fendel, right? Okay, now so basically what I'm going to show today is a simplified version of Bush and Fendel's analysis. Bush and Fendel did not assume the Lewis number equal to 1, okay? But I'm going to assume Lewis number equals 1, just to make it simpler. But the point is that you can, if I didn't do that, the analysis becomes only algebraically more complicated, okay? So we want to try to remove algebraic complexities by doing that. But Bush and Fendel did it with Lewis number. Okay. Anyway, so this is the reaction is presumed to proceed by a one-step process, fuel plus oxygen going to products, okay? And the chemical reaction rate is given by this expression. As I said, this is actually the concentration of oxygen, concentration of the fuel, times, this is exponential OU or RT. So this is a frequency factor, concentration of oxygen, concentration of fuel. So we have assumed that the reaction is first order with respect to O2 and first order with respect to fuel. All right. Now I want to point out that there are papers in the literature where they put non-integral powers. For example, you'll see that sometimes reaction rates are written WCF to some nth power, and okay, CO2 to some nth power times B exponential, okay? So it's a non-integral powers. But in principle it's not necessary because chemical reactions do not really occur because of molecular collision between fuel and oxygen. So you might as well put that equal to 1, okay? And include all their variation in the frequency factor B, for example, or in the activation temperature, okay? Okay, so this is perfectly okay, general enough, right? Okay. So now we are looking at this problem here. Okay, this is a laminar flame. So you can see that. I'm sorry, this is an error. That must be a U. Okay, that's not a B, but that's a U. Okay, so you can see that this is the concentration of oxygen goes in. Initial concentration YO2U decreases. This is the concentration. This is fuel. Okay, this is the burning velocity VU. The temperature goes up and turns around and goes to TB. Okay, so that's the same temperature. Now the system is adiabatic, and the reactants of excess oxygen. Because of excess oxygen, there's leakage of oxygen. So this is YO2U. It leaks through the reaction zone. Okay, there's complete consumption of the fuel. Oxygen leaks. The reason why it leaks is because this is excess in oxygen. Okay, right. Now, you can take the reaction zone and subdivide it to different regions. I mean, there is this is the preheat zone over here. This part is the preheat zone. can see that it's called preheat zone because the heat conducted upstream is used to raise the temperature of reactants. This is the reaction zone, okay? And this is the post-flame zone, the bait behind it. In the post-flame zone, the system has achieved thermodynamic equilibrium, correct? And then and here, of course, the temperature is increasing, reacts at thermodynamic equilibrium. One important thing I want to point out, which is not appreciated very well, is that the premixed flame is an initial value problem. It's not a boundary value problem, okay? And mathematically, that's very significant. What an initial value problem is, what a boundary value problems are, okay? Why is this an initial value problem? It's an initial value problem because you only have to specify initial conditions. This is thermodynamic equilibrium. You're not allowed to specify that boundary condition at all, okay? You're only allowed to specify the initial conditions. Therefore, this is strictly an initial value problem. And that is the key distinction between diffusion flames and premixed flames, okay? Diffusion flames are boundary value problems mathematically. These are initial value problems, completely different character altogether, okay? Right. Okay, now in the reaction, the chemical reaction takes place in the thickness of the reaction is delta, because I already said that, okay? All right. Now this is the equation for the fuel. You can write the equation for the fuel. This is the equation for the oxygen consumption, okay? Chemical reaction rate, and this is the energy conservation equation, okay? So you can have the convective term, the diffusive term, chemical reaction, consumption, convective, diffusive, chemical reaction, and the same thing over here, okay? All right. The Q is the, so now define, W is the reaction rate, okay? Molecular weight of fuel, molecular weight of oxygen, heat capacity, okay, those are the various terms. All right, now, the initial conditions for this polymer is y tends to infinity. As I said, this is what you're allowed to specify. Y tends to minus infinity. YF equals YFU. YO2 equals YO. These are initial conditions, okay? T is TU. And after combustion takes place, these are thermodynamic, basically. Okay, TB is a thermodynamic quantity. All right. Okay, so that's the formulation of this. All right. So what is the aim of this? The aim of this analysis is try to determine m dot, the burning velocity. So this is what we're trying. Given the reactants, okay, what is the value of m dot? Okay, and we shall see that mathematically this is so-called eigenvalue problem because they are one more boundary condition than necessary is applied, and because an extra boundary condition is applied, the solution can the system can have solution only for a particular value of m dot, and therefore that's an eigenvalue problem. Okay, right. Okay, so now we need to again the classical asymptotic analysis. We need to find characteristic length scales. Okay, characteristic length scales. Now this is the characteristic length. So this is the non-dimensional C. Okay. Now, what is this particular integral? Well, you know, it's integral. I mean, you can assume, if you assume that lambda and Cp are constants, right? If you assume lambda and Cp are constants, it's simply m dot Cp over lambda, okay? And this has units of 1 over length. No. So the length scale here, in this particular problem, okay, is actually the length scale that's used, L, is lambda, okay, over m dot, okay, over Cp. That was Cp. Okay, so that's the length scale, all right? Now, what is that length? That turns out to be the length of the preheat zone. So, it's the length of this layer. That is the characteristic. So this is obtained from a convective diffusive balance. This particular length here, length scale, is what is used. So that is the characteristic length scale in this particular problem. Okay, it's not the reaction zone thickness, but the preheat zone thickness. Okay, that's the fuel mass fraction, normalized. This is the O2, and there's a reason why this is for this is the stoichiometric value. So is normalized with the stoichiometric value of O2. Okay, and that's the tau, initial temperature. You can see that this tau goes from 0 to 1. Correct? 0. Okay. All right. So now, so the equation describing the flame structure. Now, this is the equation that once you take this and substitute into that equation, this is what you get. Okay? That's the equation. Now, of course, I have used this relationship that YFU times Q. So this is the initial mass fraction of fuel times the heat release must be equal to Cp minus Tb minus Tu. Okay? So now, so this, the central point is that this is now the energy conservation equation that appears, all right? And here, this quantity lambda is this. Now, this lambda actually is the Damkohler number. So this is like this is a Damkohler number. The flow time of this Damkohler number is given by the burning velocity. That's the flow time, okay? And the chemical time is given by the B, which is so it's actually B minus 1 is the chemical time. The velocity appears in the denominator, so actually TF goes in the numerator. So this is like a flow time to chemical reaction time. And so that's the Damkohler number, the activation energy, and that's the non-dimensional form of the equation. All right. Okay. All right, and then I can take again. That's the energy equation. I can do the same thing, but it turns out the species equation will also satisfy something similar. If you non-dimensionalize the species equation, get the same form, except that you're going to get a negative sign here. Okay. So y equation yf will be this replaced by yf, that replaced by yf, and this replaced by minus. Okay, so that's the equation for yf as well as yo2. Okay, so it turns out that you can again form coupling functions. That's what Williams talked about yesterday was very important. So these are the coupling functions. You can form the coupling functions by adding the fuel equation and the temperature equation. And then these are the initial conditions. C goes to minus infinity. You should satisfy that. Okay. Now it turns out that you can integrate those equations. So you get that the post-flame zone condition must be satisfied. If you integrate this, you get this relationship. Now, so it's important. Now, this particular relation, tau plus yf equals 1, and tau plus yo2 equals 1 plus yo2. This holds everywhere in the flame. Throughout the flame, this is true. Okay, because this is we have actually coupled it, removed the chemical reaction. This is an exact solution. Okay, so this is what happens. Okay, everywhere this is true. Okay, so now that I have done now I can write yf is 1 minus tau. You see, and yo2 is 1 plus yo2b minus tau. So I can plug it here. So now I get an equation only in tau. Okay, you can only so it's necessary only to solve one equation, because the entire equation in terms of tau. Okay, well, okay, all right. So now this is the key slide which I want you to understand. Right now, there's a lot of information here in the next few slides. Okay, so now this is the energy conservation equation that's written. Okay, now I want you if you look at that equation, there is a problem with this equation. And what is the problem? The problem is that when you go to minus infinity, okay, which is very far away, okay, if you go to this, that's the central issue which people have been worked on for many years, okay. So the point is that so this is this temperature profile, okay. Now when you come very far away in this direction, this is tau, so this is tau equals 1, and here tau equals 0. Okay? So what you notice is that when you go very far away, extremely in this direction, okay? Here tau is 0, and what about the gradient? The gradient d tau, if it's d tau dc, okay, is also 0. Not only the value is 0, but the gradient is 0 as well, as you go very far away, okay? So when you do that, now if you observe this particular equation, the first derivative, this goes away, okay, and so does the second derivative in this limit. They both go away, okay. But you still have this term, okay. Now that term is not 0, all right. So now it tells you that this is 0, this is 0, but this is a finite number because I know the initial temp, so I can put a TU over here, okay. And I know what TB is. I can estimate that. So that is the problem. The problem is that this equation is not balanced, okay. At minus infinity, it doesn't work, okay? So mathematically, it's not properly posed the way it's written. So that is the central issue in combustion, in laminar flame theory, is this so-called cold boundary difficulty. Okay, the cold boundary, the equations do not satisfy, okay? Now there are several approaches. So the way the laminar flame theory developed over the ages, starting from von Karman, Hirschfelder, okay, that was the von Karman perhaps was the first person, one of the earliest person who tried to put laminar flame theory as scientific formulation. Okay, that goes even before Zeldovich. So that has plagued scientists for the so the problem is how to remove this cold boundary difficulty. That has been one of the central issues in combustion theory. Okay, all right. I'm going to tell you. Okay, now and this is actually what Zeldovich. This is Zeldovich's work. Okay, so I'm going to say that first. I'm going to continue later on. Okay, what Zeldovich said that he said that the activation energy. So you can see this particular equation can be written here. I'm just taking this particular term. That's the problem term, right? Now, if you put TU over here, this term doesn't disappear, right? But it can disappear if you assume that if you say that the activation energy is large. If you say this is very large, okay, then as you go, it can asymptotically goes to 0. Okay, so at minus infinity, it can if you say this is large, this particular term, okay. Here, what's happening here? Oh, I think I'll run out of this. Maybe I should use this one. Okay. Now, if you say that this is large, the limit that goes to infinity, treated as 0. This particular term. So that's the way Zeldovich. That was the most important contribution of Zeldovich. That you remove the cold boundary difficulty, claiming that the activation energy is indeed large. All right. Okay. Okay. Oh, here's the go. Okay, so now I'm going to talk about the cold boundary. So I'm going to go back in history and tell you how, probably tell you how old I am as well, but anyway, it doesn't matter. I go back in history and say that how this cold boundary difficulty was removed. Okay, right now, one way to do there are many ways to do that. You place no restrictions on the value of the Damn-Coulomb number or the activation energy. There's another way to say activation energy, Damn-Coulomb number is large, but activation energy is not large. Or you can say both the Damn-Coulomb number is large and place no restrictions on activation energy. So this is actually activation energy asymptotic theory. This is Damn-Coulomb number asymptotics. This is rate ratio asymptotics, activation energy asymptotics, and this is not asymptotic theory. Okay, so these are historically the way this was removed. Okay, so what Hirschfelder and Hirschfelder said the following. I go back and further to Malade and Le Chatelier and von Karman. So what Malade and Le Chatelier said, 1891, and von Karman. What they postulated was the existence of an ignition temperature. They said that there is an ignition temperature, okay, and if the temperature of the system is below the ignition temperature, no reaction takes place. Is above that ignition temperature, reaction takes place. So in other words, artificially, you can say that there's an ignition temperature somewhere over here, okay? And then say that if you go in this direction, there's no reaction. In this direction, there's a reaction, okay? Or alternatively, you can put the ignition temperature over there. So therefore, there's some sort of an arbitrariness in the selection of the ignition temperature. And that's exactly what, that's what Malade and Le Chatelier, as well as actually von Karman was the one that proposed this ignition temperature concept, okay? But the unsatisfactory part of this ignition temperature concept is that there's no way to say what that ignition temperature should be, okay? And the other analysis was by Hirschfelder, who instead of saying, he said his idea was that if you take any flames, they're always stabilized on the burner, okay? So if you stabilize the flame on the burner, there are always heat losses. That means the gradient of temperature is not zero, okay? So the temperature gradient is non-zero. So Hirschfelder said that, well, ignition temperature is not right. In fact, it is the gradient of temperature that is non-zero, okay? So, but actually it turns out they're both equivalent. So that was the argument for quite some time between von Karman and Hirschfelder, which is the right approach, okay? All right, okay. So now, then the major breakthrough came in by Zeldovich and Prof.Kalyanasundaram in 1938. They said that the activation energy is large. They had the distinguished limit of large activation energy and large Damn-Coulomb number, and by seeing the limit of large activation energy, the chemical reaction decreases exponentially. Okay, so that's removed. That was a wonderful solution to the flame theory problem. Okay, so that then immediately say that the pre-heat zone is frozen, but this is the central thing I want to tell you, that the burning velocity is an asymptotic concept. It exists only in an asymptotic sense. Okay, there's no, so this is something that has to be recognized, because people who claim to measure burning velocity should know that it only exists in an asymptotic sense. Because it exists, so they're almost always trying to measure something which only exists in an asymptotic way. Okay, and there could be several definitions, and they're either all right or all wrong, but they cannot be all wrong. Okay, they're just different definitions of. So this is a very important point I want to drive today, is that burning velocity exists only in asymptotic. It's only an asymptotic concept. Okay, just like in boundary layer theory, the inviscid flow. Okay, you have this inviscid flow and viscous flow. The inviscid flow is only an asymptotic concept because only in the limit of viscosity is zero. You can argue and say that, well, viscosity is never zero. Yes, it's not zero. Okay, but you can say the viscosity is less than a certain amount, it is zero, right? Same thing holds here as well. Okay. All right, so this is the fundamental basis of asymptotic analysis. Right. Now, in the dam column number, so in the rate ratio asymptotic analysis, we say something similar. Okay, when I say because I've been involved in the development rate ratio asymptotic for many years. Okay, so what is said here is that there exists something called the crossover temperature, and this crossover temperature is the same crossover temperature that we encountered in this hydrogen ignition problem. Okay, there does exist a crossover temperature, and unlike the von Karman's definition of the ignition temperature, which does not have a fundamental basis, this crossover temperature has a very fundamental basis. Okay, we can derive from fundamental physics the crossover temperature, and the point is that if the temperature is below the crossover temperature, chemical reactions do not take place, and the temperature is above this crossover temperature, chemical reactions take place. So that is the most important concept which comes out of rate ratio asymptotics. Again, so in addition to the burning velocity, the inner layer temperature, or the crossover temperature, is a fundamental property of the flame. Okay, right? And then, so unlike the activation energy asymptotics, where the preheat zone is frozen. Why is the preheat zone frozen? Because the preheat zone is frozen is because the both fuel and oxygen exist, but they don't react because the temperatures are too low. Whereas here, we say that the preheat zone is frozen, not because the temperatures are low, because no radicals exist. There are no radicals, because radicals have been removed because the temperature is lower than the crossover temperature. As a consequence, the preheat zone is inert. Okay, that's the right. Okay. Okay. So now we're going to go. So this again, these are important points which I want to emphasize. Now we look at the. So now again, I said now we're going back to activation energy asymptotics, which is large activation. So I'm going back to this. Okay, this particular formulation by Zeldovich and Frank Kamenetsky. Right. And now we say that the activation energy is large. So now the flame has two zones, an outer zone. So this is the outer zone over here. This is the outer zone, which is the preheat zone. Okay, and there's a thin reaction zone. Okay, in this outer zone, it's frozen. Okay, and therefore the chemical reaction rates are not in, chemical reactions do not take place. And there's a balance between convection and convection and diffusion. Okay. It's a simple balance. So this is the so-called, sometimes this outer zone, which is a frozen preheat zone, is also called a convective diffusive zone. But in this zone, there exists a balance between convection and diffusion. There's no chemical reaction. Okay. So now we can solve this. So we can solve this equation because remember, so this is the solution to this equation. All right. How do I get that? Because you see, if you look at this. You see, the idea is that if you look at this here, tau must be 0 over here. So you can see that C tends to minus infinity, which is here. This is C minus infinity. Tau is 0. And when C is over here, which is C, this is a reaction, so this is C equals 0. So at C equals 0, this is 1. So therefore, the temperature profile goes from 0 to 1. Okay? So that's why we are captured. So basically, the outer zone is so this is what, as far as the outer zone is concerned, the reaction zone is very thin, okay? The temperature profile, comes in life, okay? That's the temperature, that's it. Okay, and this is what, that's it. This is 1 over here, and this is 0, the temperature profile is 0, this is 1, okay? And the reaction zone is asymptotically thin. Okay, that's the outer zone analysis, all right? Okay. Okay, so now, so that's YF, now, you obtain this from the coupling functions, okay? We had talked about the coupling functions before. That's how you get YF, okay? And that's YO2. Now, in the post-flame zone, of course, the chemical reactions are in equilibrium, and tau equals 1, right? So that's, again, I said that is the outer. So now we have, but remember that in this particular formulation, the burning velocity is not there, okay? It has disappeared, okay? We have gotten the temperature profile, but now to get the burning velocity, we got to introduce chemistry back into because the burning velocity depends on the chemical reaction rate, so we got to force the chemistry back in, okay? So now we got to do stretching of the equations such that chemical reaction terms reappears, right? Okay. Okay, so now this is what is done here. So now I'm going to, just like boundary layer theory, you have the outer zone, okay? The inviscid zone, the analyzed inviscid zone. Now we got to go into the boundary layer, okay? So now we're going to focus on this particular thin reaction zone, which is here at C equals 0, right? So now here comes the stretching. I mean, now we have to need to expand this. Now this is C equals 0. So now I have to expand this. Okay, to look at that, I got to expand that, right? And therefore, you define a quantity eta, which is you define an eta, okay, which is a C over epsilon. Okay. So that's what is done here. Now, so this becomes a quantity of order unity because in the reaction zone, C is 0, and then you have this epsilon, which is very small. You take the ratio of two small quantities, and you get eta, which is of order unity. Okay. So this is the independent variable, and as far as the dependent variable is concerned, as I said, this is tau. So now I want to get a profile. So now I want to get a profile which is like this here. We get that, okay? So now this quantity here, this difference here, okay, is this difference over here is going to be my epsilon times y. Okay, so the temperature is decreased by this amount epsilon y. Okay, so there's a leading order term correction over there. Okay, and that's eta. Okay. Now I can see that the tau is being 1 minus epsilon times minus y. If you recall, I said that everywhere in the reaction zone, tau plus yf equals 1, okay? Therefore, it follows that yf is 1 minus tau, and since tau is 1 minus epsilon y, yf has to be equal to epsilon times y. Okay, right? So that's the concentration of the field in the reaction zone, okay? And that's the constant, that's YO2, obtained in a similar fashion, all right? And now we get, if you take this equation and expand this, you get this. You can see that remember that tau is 1 minus 1 t minus tbu divided by tb minus tu. You put that over there, okay? You can see that the temperature is given by that particular expression, all right? Okay. So now, remember that my aim of this analysis is to force the chemical reaction terms back in, okay, into that, okay. So now you have this exponential e over RT. Instead of t, I'm going to substitute t, this expression for t, okay, and you make a Taylor, and as I illustrated before, you make another Taylor series expansion. You make a Taylor series expansion for small epsilon, then of course, remember that there's a t, you can pull the tb out. So it's going to be 1 minus epsilon y over tb. That's what appears in the denominator. Okay, and then you make a Taylor series expansion of that. Okay, and this is the result that you get. Okay, so this exponential term is this, and here and that. There you can see that there what appears here is the Zaldawish number. It's very. I think I should show that because that's a very important point there. Okay, so if you take let's see. If you take t, 1 over t, you write that as 1 over tb, okay, times 1 minus epsilon y over tb, okay, tb minus tu. Okay, that's minus 1, okay? So I do a Taylor series expansion is 1 over TB, 1 plus epsilon y, okay? TB minus TU. So this is going to be equal to 1 over TB plus epsilon, epsilon y, TB squared, okay? TB minus TU. Okay, that's what you get, right? Okay, that's what that is. All right. So you get that over there, okay? Now remember that this is all multiplied by E over R. There's an E over R that appears in front, okay? So if you multiply that by E, if I put an E over R on this side, if you add both, if you put E over R on both sides, okay? Then you can see that the Zeldovich number appears. You can then naturally this quantity epsilon, okay? Now you can see this quantity Zeldovich number automatically appears over there. Since you can see that the Zeldovich E over R, TB minus U, that's the Zeldovich number right there. So you can see that the Zeldovich number appears in a very natural form here. Okay. Okay. Right. Okay. So now again, if you introduce expansion into the full into this difference, so what I've done here is I've gone back and taken these expansions, okay, put it into the full differential equation, which is here. Put it into this differential equation, okay. When you do that, you obtain, okay. Oh, I'm going backwards now. Okay. You get this equation, okay. This is so now you notice something very interesting here in this particular equation. This again we want to emphasize. You can see that the epsilon appears in front of the convective terms. Since we have said that epsilon is small, we can drop this, so the convective terms can be dropped. So now that's a diffusive term, so now your balance. So in the reaction zone, it's called the reactive diffusive layer because there's a balance between diffusion and chemical reaction. Okay. Now if you look at this, so I can drop that, but now this is a diffuse. Now I must keep this term because the reaction rate term must be in that equation. Okay. So now we have some selections. One way to keep that, you have to say something about this here. Okay. We cannot say this is very large. If this is very large, the entire term drops. Okay. So what you say is that Zeldovich number times epsilon, you have to say this is 1. Okay. So this forces this exponential term to be, there in the equation, okay? So now the epsilon is selected, actually epsilon is 1 over the Zeldovich number. But then if you put it over here, in this particular equation, okay, then we must also have this to be of order unity, okay? Because this must also be of order unity, so therefore that's the eigenvalue, right? So therefore now immediately see that this is a large, so this is a lambda prime, as I said before, is the Damkohler number. So now you have a large Damkohler number as well as a large asymptotic. So therefore this is a distinguished limit that appears here, okay? Right? Okay. I'm okay with time, or yeah?
I think we can go over 10 minutes.
Oh, 10 minutes, okay, yeah. Yeah, sure. Mm-hmm. I want to make, I'm not too much over time, right? Or
no, right now you're not over time.
Okay.
You can't go over time.
Okay. All right, yeah, that's good. I just want to know that. Okay. So now this equation takes this particular form, or takes this form. Okay. Now I've dropped that, and I've assumed I've selected epsilon to be this, and this. So that's the equation. Okay. So this is the equation which describes the structure of the reaction zone. Okay. Now, again, this quantity y, and this detail, I'll let you work this out, okay? Just in interest of time. This quantity y, as eta tends to minus infinity, y tends to infinity. What does that mean? It means that this because the temperature profile, the temperature profile continuously decreases, See, it's a, if you solve the structure of the inner layer, so this is the outer layer, this is the structure of the outer layer, okay? When you solve the structure of the reaction zones, so actually what it comes down, it comes like this, it's very, and then it starts to deviate away, okay? So this is epsilon y, okay? So you can see that as epsilon, as you go further and further, okay, away from the, as you go further and further away in this direction, okay, this epsilon as c tends to minus infinity, y tends to infinity, y tends to minus infinity as c tends to minus infinity, okay, because the gaps widen, okay. So therefore, y can be has this particular form, and you can show that again mathematically. This is just being mathematically very rigorous. You can rigorously show that if you take this particular equation and you in this limit and put it over here, then you can show that the problem has translational invariant. That is, if you change the independent variable from eta to eta hat, the equation will look the same. Okay. So when you have something called a translational invariance, then you're allowed to put c naught equals 0. Okay. So if you put c naught equal to 0, so it turns out y is minus c1 infinity. So c1 eta as in eta goes to minus infinity, this quantity y goes to infinity over here. So the distance will get wider and wider. Okay, that's that one here, right? All right. So that's one of the condition for this particular equation, right? Okay. So now now this is now what are the boundary conditions for this? Okay, let me go back. Okay, the boundary conditions for this. No, there are two boundary conditions. Okay, the reaction zone temperature must match. You must match to the post-flame zone over here, and you must match to the so the boundary condition for this particular equation is obtained from matching. Okay, one to the post-flame zone, and the other one to the preheat zone. Okay. Now in the post-flame zone, it's very clear. You can see that in the post-flame zone, y must be 0. Okay, so that's what this condition is. Okay. Okay, that's what this condition here is. Okay, as eta tends to infinity, which we are moving away in that direction, the gradient as well as the value is 0. So that's one matching condition satisfied. Okay. Now to match the second, to match it over here in this side, you have to use what is known as an intermediate variable. This is doing mathematically formally. Okay. In practice, often you can just look at it and write the matching conditions. Okay. But very often you make mistakes if you do that. So it's best to do these. It's best to do this using something called an intermediate variable. Now, how do you do that? Okay. Remember that the way you do that is the independent variable in this region is c. Okay. Whereas the independent variable here is eta. Right. So now you can see that the c goes to 0 and eta. So in this intermediate region where I want to match, c goes to 0 and eta goes to infinity. Okay. So that's the point. Okay. So, and that is achieved by defining a so-called intermediate variable, theta. Okay, this intermediate variable is defined like this: c divided by some function of epsilon. Okay, where this epsilon function of epsilon is much greater than epsilon, but is much less than 1. Okay, so this particular so you select epsilon, sigma epsilon, such that this inequality is satisfied. Okay. Then if you do that, immediately you can see that. Remember that in asymptotics we want this theta to be of order unity. Okay, it's neither small. So this is the intermediate variable where the matching is done. So you do the matching in the intermediate zone, and the intermediate zone where theta is defined, it should be of order unity. All right. Okay. So you can immediately see that the theta is fixed. So therefore, now I can write c in terms of theta. Okay, so you can see it here. C in terms of theta is this form. Okay, so now you can see that since theta is order 1, remember that this is very small, right? It's much less than 1. So therefore, this automatically goes to 0, right? But now recall that c is actually eta over epsilon, correct? So so now if you write eta, So the C is actually eta is C times, the way we defined eta was C times epsilon. Okay, that's the way it was defined. So now in terms of eta is just this. Okay, so now if you rewrite that, if you write in terms of eta, it becomes this. Now you notice that this ratio is very large, right? Because we have made the assumption sigma x, this is much larger than that, therefore this ratio is large. So in terms of when theta is order 1, eta goes to minus infinity like we want, because this is very large, okay? And theta goes to 0, and c goes to 0. Okay, so that's the. So in terms of the intermediate variable, c goes to 0, and eta tends to minus infinity. Okay, so now you have to write the inner equation. You have to write the equation. The temperature profile you have now the temperature profile in this preheat zone, as well as the temperature profile here, must be now written in terms of theta. Okay, because that is the intermediate variable that we have, right? And if you do that, recall that exponent. If you go back to the preheat zone solution, the preheat zone, the solution was okay here. I don't know where I had. Okay, I had it someplace. Okay. Well, I don't know. Okay. Anyway, the preheat zone. Oh, here it is. That's a preheat zone solution. Theta. Okay. And then the. Oh, okay. I'm going in the right direction. Okay. I'm sorry. And then in the inner layer, in the reaction zone, this is the solution. This is the expansion for tau in the reaction zone. Okay. So if you do that, if you put it, so this is the preheat zone solution, this is the reaction zone solution. Now I want to express C in terms of theta. Okay, so now then for small values of C, you can expand the exponential like this. That's the expansion for the exponential, and this is the 1 minus. And I want to write epsilon. Okay. I want to write this y in this particular form, okay? Then when you do that, the ones cancel, right? So therefore, so the answer that you get is y is minus eta, okay? So that's the matching condition. So the boundary conditions for this equation is y is minus eta and y is 0. That's how you get the matching conditions, right? So the matching condition must be really obtained using intermediate variables, okay? Right. Okay. Right, so now we can integrate that equation. It's very straightforward. So now, by the way, I'm not sure if you know what this is the so-called energy integral. And if you have a second, when you have a second order, maybe I should do that. When you have a second order derivative, that, for example, this d squared y, dc squared, this is what we had, okay? Remember that it turns out you can write this as half d by dc of dy dc square. That's the energy integral. Okay, so energy then if you expand that, you get that expression. Okay. Okay, it's straightforward. And if you want to remember that that's simply equal to simply equal to half. Okay, if you differentiate, it's going to be 2 dy. So okay, this is dy. No, I'm sorry. Let me erase that. Okay, this is important. This is actually d by dy. Sorry. Oh. This is d by dy. Okay. So what this is d squared y dc squared is half d by dy dc squared. Okay. So now if you want to differentiate, okay, you can see that is indeed correct, because I can write that as half d of dc, okay, of dy dc squared, okay, and then dc dy, okay. Now to differentiate that expression, the differentiate is going to be 2. There's already 2 over here. D squared y dc squared, okay. Okay, half, yeah, times dy dc, correct? Okay, and then you have a dc dy. So these cancel, that cancels, so you get the second derivative back. Okay? So this is the, so that's the classical, that's the classical, that's the classical you can write the second derivative in this particular form. So if you write it in this particular form, then it makes the integration very easy, because okay, I'm sorry, I don't know what I meant. Okay, no. Okay. I'm going to a different problem altogether. No, okay. So you can see that. So therefore, that's the side. Oh, this is the left-hand side. Okay. So which is that? Okay. Okay. Here. Yeah. This that particular equation. Okay. This is written in that form. Okay. So now you get that particular integral. So you get this expression, right? Now it is possible to integrate. Now boundary conditions are that at minus infinity that the y has to be 0. Okay. And then y is, so this is the boundary conditions, y is 0 at minus infinity, is 0 over here. You can integrate it. So now you can integrate this expression. Okay, and again, for students you should try to do that integral. Okay, so you have to do that integration by parts. It's possible to evaluate that integral. Okay, then you get this. Then you get the eigenvalue lambda as this. All right. So now if you remember the eigenvalue lambda contain the burning velocity, you get this final expression for the burning velocity from asymptotic theory. Okay. So notice that a lot of similar. So this is the asymptotic expression for the burning velocity, and you can see that we did that from phenomenological analysis, a very simple analysis. We had the burning velocity. They're very similar. Okay.